Okay, thanks again. Um, okay, so let me start by summarizing a bit what we discussed last time, because that will put us in a good position to continue. Last time we computed we explored the geometry of near-extremal black holes. And we saw that by computing their on-shell action and their mass, we saw that near-extremal black holes have a mass that near-extremality takes an extremal value that's simply dictated by the charge. The charge can be arbitrarily large, and these black holes can be arbitrarily big. But the deviation in the temperature starts scaling as t squared. And the important parameter here is this breakdown scale, which in terms of the charge of the black hole is given by 1 over QQ. So it scales like, if you remember, the extremal entropy of the black hole scaled like pi q squared. This was also a formula that we had last time. So we can think about this breakdown scale as 1 over S naught being suppressed and 1 over S naught to the 3 halves in units of M Planck. So it's a very small energy scale, but we saw that below this energy scale, so when we're very close to extremality, the black hole cannot seemingly radiate even a single Hawking quantum. And this can be viewed as a breakdown of thermodynamics, because in thermodynamics we assume that we can radiate where in order to get to equilibrium, to change the temperature a little bit, we have to radiate an infinite number of degrees of freedom. And this led to 2 puzzles. Puzzle 1 was, what happens really close to extremality? How can we resolve this breakdown? Are there like very large corrections to the naive density of states that we get from the semi-classical calculation? And puzzle number 2 was a related puzzle, which is that seemingly this semi-classical calculation shows us that the extremal entropy can be arbitrarily large, because we can scale the charge to be arbitrarily big. And there's no an extremal entropy implies that there's a huge degeneracy for the ground state in the charge sector with charge Q. And there's no real symmetry that protects the degeneracy. So how could that be possible? So that was question 2. And a related puzzle was that we saw some trouble with when trying to build up the duality between gravity in 2-dimensional anti-de Sitter space and a 1D CFT. Namely, we started by looking at a 2D IPhT that arose from the dimensional reduction in one of these black hole backgrounds, where that was written in terms of a dilaton field that we called chi. It was 1 over 4g Newton, 4d, g2x for g I times r, plus a potential u of pi, plus couplings between matter fields and the metric and the dilaton. But in the near horizon region, we saw that we could expand the dilaton chi around its extremal value plus some small deviation. And this gave rise to a much simpler gravitational theory, in which we simply have one term that's the analog of the Einstein-Hilbert term in 2 dimensions, multiplied by phi 0. Phi 0 here is essentially the radius, thus area is proportional to the area of an extremal black hole. And phi captures fluctuations of this area. In the transverse direction. So this effective theory that we get by doing a first order expansion in phi 0, the area of the extremal black hole only varies, the areas in the radial direction around the extremality only varies very slowly. So we can expand this action for large phi naught, or phi naught much bigger than phi. And we saw that we got a 2D theory, which is also known as JT gravity. So JT gravity is like the effective field theory for the massless degrees of freedom in the near horizon region of a black hole when you dimensionally reduce. In addition to this, there is degrees of freedom that in general either have masses that scale like phi naught, or there are corrections that come from the dilettante potential that are suppressed in 1 over phi naught. Okay.
That's a real danger.
Okay, and the metric here, writing down the equation of motion for phi immediately tells us that in the near horizon region, it's a good approximation that the space, immediate solution is just ADS2, whose metric I'll just write here for in the near horizon region. I just last time we saw that it takes this form. Okay. And what was wrong with this theory? Well, if looking at this theory in Lorentzian signature, so here I'll draw a Penrose diagram of an ADS2 Poincare patch in Lorentzian signature, whose metric one can rewrite through a diffeomorphism as d minus dt squared plus dz squared over d squared. What we saw is that if I want my dilettante to take a finite value at the boundary, the only option by solving the equations of motion of the metric for this action, the only option was to set the dilettante equal to 0, which means that asymptotically I'm forced to consider if I want to consider asymptotically the dilettante going to 0, I have to fix the dilettante to 0 on the entire space-time as d goes to 0. But there was a problem with this. Namely, if I inserted the lightest possible energy excitation into the system, say here, I insert a stress tensor who's given by delta E times delta function in V. V is the Lycombe coordinate. That's a combination between T, the appropriate combination between Z and T. I saw that on any point to the future of this insertion, the dilettante blew up on the boundary. Good. So that means that back reaction for the near horizon region of an extremal black hole is completely out of control.
Sorry,
In the last lecture, you showed how this happens. Can you just give a brief reminder of how well this happens?
Yes. So you solve the equation of motion for
In ADS2.
in ADS2. So you look at the equation of the variation of the action with respect to the metric. You get the an equation of motion that involves the dilaton. You solve the equation of motion for the dilaton, and since you asked, I'll just rewrite the solution. So phi is a function of u and v. Here, I hope I remember correctly, u is t minus v, v is t plus v. Let's see, u minus v. Yep. No, this is v and this is u. Phi is the function of u and v. We found that it depends on arbitrary constants that should be set by the boundary conditions that we impose on the dilaton. So phi of u and v takes the form a tilde plus b tilde u plus v minus mu tilde u times v divided by u minus v. U minus v is proportional to z. So this factor is divergent as we approach the boundary. So the only way to set the dilaton to 0 in the geometry is by setting all these constants to 0. Now, when I insert this shock wave, what essentially happens is that I can solve the equations of motion once again when I couple this theory to matter. And what changes is that if before these constants were
We have been warned. Don't worry. There is an example.
Should I continue?
Stay here.
Évacuation générale du bâtiment, enfin de l'installation. Évacuation de l'installation.
Maybe you could write no panic.
It's an exercise that you have to do every once in a while, you know. The two reactors nearby, one of them blows up, you know, you're supposed to know what to do.
Immediate evacuation of all personnel from the buildings.
In the lobby,
I
if
see.
there's radioactive fallout, then you stay inside. If there's not, then you go outside. And they tell you, you're never supposed to go outside because, you know, maybe there's
Exactly. I was surprised because he said that we would go outside.
It depends on the simulated event. If there is a radiation, you stay inside. If there is a fire,
Going outside.
yes.
Just so that nothing happens.
No, let them go outside. You're not supposed to go.
We had
we are in a
you are
bubble.
late, but there was a rush which informed us that there is a security exercise and that we may accept and stay here and
Because of our
continue
course.
the seminar,
Yes.
the course. So it was nice.
The video evidence of all of us disobeying.
No.
If you want.
It's an exception. They're protected by, I mean, it's the boss.
I guess that maybe for 5 minutes you can go.
No.
Yeah. All right. So yeah, the idea was that when you turn on this matter source, the equations of motion, here are the same. The solution is the same. You just have to glue the solution past this light cone to the solution before this light cone. The only thing that could change are these constants, a tilde, b tilde, or u tilde. You could find what, in this case, I think u tilde becomes non-zero if you turn on non-zero energy stress tensor on this light cone. So if u tilde becomes non-zero, you still see that as z goes to 0 on this patch, as z goes to 0, so as u minus v goes to 0, this factor still diverges, right? So essentially, we started with a space-time was ADS2 times S2 initially. It was the ADS2 and S2 were perfectly independent. And afterwards, after inserting a small amount of energy from the boundary into the system, we find that the dilaton blows up, which means that we can no longer say that the radius of S2 is independent of the point that we are on ADS2. And this is in contrast to what would happen in ADS-CFT in higher dimensions when we send in some energy pulse from the boundary. It's never the case that in the decoupling limit in the bulk, we vary the radius of the internal space a lot. Yeah.
But here, so if I send, for example, some pulse, I mean, if I have an ADS2 black hole which is glued to flat space, and I throw in some pulse, the pulse goes into ADS2 and then falls in and then goes through the horizon and makes my black hole into a near-extremal black hole.
Yes. Yes.
I still can do that. So why is there a problem if I take the decoupling limit? So the phenomenon is the same. I throw in some S wave from infinity, it goes down the ADS2 throat. I have a huge ADS2 throat which goes on forever. So if I'm in the middle of the ADS2 throat, I see some scalar wave going down towards the and then it goes inside the black hole. It gets eaten by the black hole.
Perfect. But then you will see that in this EFT that you get in 2D that describes the theory, your dilaton blows up. Yeah, that's it.
Why does this happen in a real black hole? I mean, if I have a Resta-Nordstrom black hole, extreme Resta-Nordstrom, and I throw in some wave, it goes in and falls in, doesn't it? I mean,
it falls in, and what you see is that your space-time now changes the radius, right? So you can see in this metric, right? What happens is that as you go at extremality, at exactly extremality, this factor delta m is equal to 0. So this delta m is equal to 0. And here you have just a factor of q squared. You no longer have this thing. But when you turn on a small energy pulse, what happens is that you now get a contribution from this term, which is non-negligible. And the point is that you can no longer neglect the fact that the radius of this S2 is dependent on R tilde as you approach the boundary of ADS2. That's it.
It's not a problem with the extremal black hole per se. It's a problem about the EFT, right?
No, it's a problem. It's a problem with writing down the gravitational theory in ADS2. I think and taking the boundary conditions that that we typically consider in higher dimensional ADS-CFT.
I mean, the fact that it's exactly at extremality is important, and it's. I mean, as you've said, if you do this from the asymptotic point of view, then extremal becomes slightly non-extremal, which is the resolution of this.
Yes. So the resolution here. So what this suggests is that we should reconsider the boundary conditions for phi.
Can I say this again another way? Just tell me if this is right. I mean, this is also from the boundary point of view. In a general dimensional setup, doing this would be like a local approach, right, where we have this Hamiltonian deformation of the boundary. Here, I mean, assuming that we're at extremality, the density of space took this highly constrained form where there's not some free function of energy that I can tweak by adding a deformation term to my Hamiltonian, because it was just either delta function or 1 over e behavior. It's like very rigid. So there's no room for me to spectrum in a way which is smooth and directly related to the fact that we're exactly in ADS2.
Yeah, I think that's the CFT1 perspective on the issue. Okay. Great. Go back to where we were. Okay. And finally, puzzle 4 were various versions of the black hole information paradox that were all related to the fact that at the semi-classical level, rho of B was not a sum over fixed discrete energies. Today, we want to understand whether by changing boundary conditions to resolve this issue brought above, And by considering fluctuations in the path, by summing over fluctuations in the path integral, we can resolve these puzzles. So today, resolve puzzles. And what we'll manage to achieve is we'll show that a perturbative summation of fluctuations, of gravitational fluctuations in the near horizon region, together with the change of boundary conditions, will resolve puzzles 1 through 3. And even though it will change the form of the density of states, it will not resolve puzzle 4. In the sense that the density of states will not suddenly take the form of a sum over delta functions. So let's start by analyzing what boundary conditions we should actually consider. So for that, we want to see what if we take a near-extremal black hole whose spatial slice has a very long throat, that has a horizon at the end. What boundary condition should we consider at an arbitrary cutoff that separates this region, that's approximately ADS2 times S2, from the asymptotic part of the space-time? So we're going to ask what the boundary conditions are. For the dilaton, 5, and for the metric, mu. And I just want to remind you that here, both ADS2 and S2, the radius of curvature of these spacetimes were both set by the charge of the black hole. And namely, it was equal to Q times L prime. From now on, to simplify things a little bit, I will, I will drop these explicit units of L Planck and M Planck. So to start, we had our IPhT that was applicable in the S-wave sector on the entire geometry. It was written in terms of chi. And now we want to see what happens when we expand the IPhT around that extremal background. So what we want to understand is what happens if we deviate a little bit from extremality. What boundary conditions, how is the boundary condition for the metric at the edge of ADS2 correlated with the boundary condition for the dilaton? So here, I want to remind you that we're working in a system for which we have a coordinate that is the Euclidean time that is periodic. And the idea is I can start with my IPhT on the entire space-time and integrate fluctuations of the metric that go above extremality, integrate them by parts to capture all the fluctuations that occur outside the near horizon region by a single boundary term at the edge of the near horizon region. So we could write the total action as a sum of the action in the near horizon region. So that's the action evaluated on the space-time up to this arbitrary cutoff. We'll see that at the end of the day, the result will be independent of this cutoff, but it will help us understand that this cutoff will help us understand the physics a little bit better. So it's the action in the near horizon region plus the action far away from the black hole. And integrating this action far away by parts, we get that the action is given by I far away, evaluated on the extremal metric, and extremal dilaton profile, minus 1 over 2g Newton integral over the boundary of the near horizon region. Du square root of h. This is just essentially what you would get from the variational principle. Pi delta k minus partial n pi minus pi k delta of square root of h du. Right. So if you squint a little bit, so here delta k is the difference between the extrinsic curvature between when evaluating it on the region far on the boundary from the region far away. So it's measured with respect to this vector, this normal vector, compared to when evaluating it with respect to the near horizon region. So with respect to this vector. So the point is that previously the geometry was smooth, but if we expand the geometry outside around the extremal metric, we essentially get the CFT that glues a smooth geometry in the near horizon region to a smooth geometry far away for a junction in which the extrinsic curvature can vary. But if we want the two geometries to still be connectable, they need to have the same induced metric at the boundary. In order to connect two curves, they need to have the same proper length, and therefore the same induced metric. So this thing will be set to 0. So this term vanishes. Suppose that we define where this cutoff is by fixing this induced metric to be some value, right? So what defines this cutoff is, we can say that square root of h tau tau takes some value, which is given by 1 or L2, the ADS2 metric, over some cutoff parameter epsilon. This is arbitrary. So this proper length, if I integrated it along a curve that's at a location where r tilde was equal to r tilde boundary, then this proper length is given by integral d tau, square root of h tau tau, our boundary, which turns out to give beta times L2 times r tilde boundary. So it means that this r tilde boundary takes the role of 1 over epsilon. So the cutoff here, epsilon, is related to where I put my ADS2 boundary in these r tilde coordinates. Okay, so if these are the boundary conditions for the metric, what are the boundary conditions that we should take for pi? Well, pi at that location is simply given, we can just evaluate what pi is. Pi was the transverse area evaluated at this value of r tilde. So it's simply given at leading order by q squared plus, so q plus Q squared R tilde boundary, everything squared, which at leading order, if we say that this is much smaller than Q, is Q squared plus 2Q cubed R tilde boundary. Okay. So at the edge of ADS2, the dilaton value takes the form of pi r over epsilon. So here epsilon is 1 over epsilon is like r tilde boundary. From this we deduce that phi r, this is called the renormalized value of the dilaton, because this r tilde could be divergent. Is 2Q cubed, or it's precisely 2 times that energy breakdown scale inverse. So at this point, we should pause a little bit and notice that even if we take L to be infinite, so we take the ADS2 boundary to be very, very close to the asymptotic region of ADS2, then our dilaton will blow up more and more. But we should express things at the end of the day. We chose this cutoff region somewhat arbitrarily, so all our final results we should check that all our final results should be independent of epsilon, which means if they are independent of epsilon, then I should find the ratio between this proper length and this value of the dilaton that I fixed at the boundary of ADS2. I should find a combination of the two that's independent of epsilon. Well, that combination is obvious. So if I try to form a dimensionless combination of out of these two values of the fields at the boundary, the only possible thing that I can write is L over phi b divided by L2. So this is dimensionless and independent of the cutoff, so of R tilde boundary or epsilon. And it's precisely given by the ratio between the breakdown energy scale that we encountered earlier in puzzle 1 and 2 and the temperature T. So this is like a measure of how close we are to extremality. So essentially, the fact if everything would be self-consistent and independent, and when I try to find what the path integral is, I should find that the answer is independent of the way I separated these two parts of the space-time. It's just a useful mathematical trick. I should find that all answers only depend on this ratio, which is very encouraging. The other important point that we can see is that even if I consider an extremal black hole at the edge of ADS2, I should still consider a dilaton that is divergent. Fantastic. So now, what we want to do is write down what the total action is when we sum up the action in the faraway region and the action in the near horizon region. In the faraway region, we just expanded around the extremal metric. So the only thing we have to do is evaluate. What the on-shell action in that faraway region is on when inputting the extremal metric and extremal profile of this dilaton. So what one finds is that the action far away is simply given by beta times q. So even though we inputted the extremal metric and extremal value of the dilaton, the time direction is still periodic and has period beta. That doesn't change even though we input parts. So the action is still beta dependent, and it can be expressed as this simple term beta q, where you might identify this term as precisely determines the log of a partition function that captures the contribution of the extremal mass. And then in addition to that, there's a cutoff dependent piece, which can be expressed as an integral over that cutoff region of du square root of HU times q squared. Now, on the other hand, the extremal extrinsic curvature, when measured with respect to the normal vector that points from the outside, is also easy to calculate, and it's just given by 1 over the radius of ADS2, or 1 over 2. Okay, so let's now write our total action once again. So in total, we find that it's given by beta times m naught minus a quarter integral d2x square root of g pi naught times r minus half integral d2x square root of g pi naught times k, measured with the extrinsic curvature of measured with respect to the near horizon region, minus a quarter integral d2x square root of g phi times r minus half integral d2x square root of, oh, sorry, this is not d2x, this is just du square root of HU. Du square root of HU times the value of the dilaton fixed at the boundary, so phi r over epsilon, times delta k, which is the difference between the extrinsic curvature measured outside and the one measured from the inside. Okay, so this is my effective field theory for the near horizon region that takes into account the correct boundary conditions at the edge of the throat. And here I can see that it consists of two terms. A term that contains phi naught that we'll identify in a second, that is essentially a version of the Einstein-Hilbert term in 2 dimensions that has a Gibbons-Hawking-York term in order to satisfy the variational principle with fixed boundary conditions, and a term that couples the curvature to the dilaton that also needs a Gibbons-Hawking-York term in order for the variational principle to be well defined. The difference, by the way, is the fact that here the dilaton is multiplied by the difference of the 2 extrinsic curvatures on the inside and outside, versus here, where it's not, is the fact that in the region far away there was this additional term that precisely canceled this contribution that would otherwise have been subtracting here, would have subtracted the k in the near horizon region by 1 over L2. Okay. Fantastic. So now what we'd like to do is understand this action a little bit better. So first, let's understand the top term. Well, if I pull phi naught in front of everything, one can recognize that all these terms essentially are fixed by Gauss-Bonnet's theorem in 2D. Namely, half of the integral of R plus integral of K is what gives you the Euler characteristic of a manifold. Here we're just evaluating the Euler characteristic of the area of the near horizon region in Euclidean signature. That's just a patch of ADS2, so that's like a disk. So the Euler characteristic is 1. So overall, this contribution precisely gives you 2 pi, gives you pi times phi naught. Phi naught was the area of the black hole at the horizon, of an extremal black hole at the horizon. So this was equal to pi q squared. So this term, term that's essentially a topological term in our EFT, captures the entropy of an extremal black hole. So what we should expect is that the other terms capture the corrections above extremality, right? Which of course should be the case because that's precisely what this dilaton phi, the variation of the dilaton above phi naught, should capture. Good. We can, again, as we did a couple of days ago, we can integrate out, oh, I forgot that this R is multiplied by R minus 2 divided by L2 squared. Okay, so as we did a couple of days ago, we can integrate out R, or sorry, integrate out phi. Essentially, it's like a Lagrange multiplier, which sets R equal to minus 2 over L2 squared. Which is, again, just ADS2. So the only thing that's not fixed in this equation, the action of this is set to 0 by the fact that R is set to minus 2 over L2 squared. The only thing that's not fixed is this boundary term. So the point is that with the boundary conditions that we've specified, we haven't actually fixed the location of the junction between the near horizon region and the far away region. What is not fixed is the boundary curve of ABS2, which if I rescale if I now work in units where I set L2 to 1 and work in a metric in the simple Poincare coordinates for ABS2. What is not fixed is the shape of a curve, of the boundary curve, that's characterized by some t as a function of a proper boundary time tau, and z as a function of a proper boundary time tau. So essentially in the upper half plane, this is t, and this is z. I can consider a boundary in a patch of ADS2 whose boundary takes any shape. So this is a boundary of the near horizon region. Good. So the only thing that this boundary has to satisfy are the boundary conditions that the induced metric along the boundary is fixed. So the induced metric is very large, right? Because it has a factor of 1 over epsilon. So this implies that this boundary curve wants to live very close to the z going to 0 boundary, asymptotic region of ADS2. But we want to consider fluctuations of this boundary term that occur because we're not setting the induced metric to be exactly infinite. We want to keep track of how the induced metric scales with the cutoff. And we'll see why that's important in a second. Okay. Any questions? So now we're just left, the only piece in the action that we haven't evaluated is this piece. So we want to evaluate this piece of the action for an arbitrary shape of the boundary that obeys the boundary conditions that we imposed. So the extrinsic curvature, you can just evaluate it in Mathematica by using the definition of an extrinsic curvature. The extrinsic curvature can be written in terms of T and Z. When T and Z are parameterized by the proper boundary time tau. So specifically, the formula that this extrinsic curvature takes is a bit ugly in terms of T and Z, but let's write it. Good. And now this is a formula that's applicable for any curve that's parameterized by T and Z. So the only thing I need to impose is that the induced metric is 1 over epsilon. So the induced metric in terms of T and Z is given by T dot squared Z prime squared divided by Z squared. Just following from the form of the metric in 2 dimensions, right? So if I work in the limit in which epsilon is a cutoff that is very small, this implies that the parameter T and Z are related, right? Namely, to leading order in epsilon, one finds that Z of tau can be expressed as epsilon times tau prime of tau, which means, as T is changing along this direction, as it's parameterized by tau, Z changes a little bit, but it's still very close to the asymptotic region of ADS2. So it's very close to Z going to 0.
How do you get this relation between 1 over epsilon squared and T prime plus Z prime?
Oh, this is just a formula for an induced metric.
Are you just setting the conformal class of the induced metric? Is that what you're doing?
So here I'm choosing to parameterize my boundary by some proper time tau, right? And I'm saying that, okay, I can describe any curve in ADS2 by, choosing some functions C of tau and Z of tau. And then one can write what the induced metric on this curve is as a function of these two functions. And,
Why don't you identify this as epsilon? Because this induced metric, I mean, why do you identify this as epsilon?
Because that was the boundary condition that I fixed at the edge of the near horizon region, right? Like I determined what h tau tau is by looking at the faraway region, solving the equations of motion here. And this fixed two things at the edge of the probe. It fixed what the metric is, and it also fixed what the dilaton is. So delta chi or delta phi is equal to 0. Here by delta chi or delta phi, I'm just indicating that these are the boundary conditions that I'm setting. And specifically, if I worked in tau coordinates, the induced metric from the outside that I got was this h tau tau was equal to L2 over epsilon square root.
That's a number.
That's a number that depends on the exact cutoff that I input. And I want to match, I can only write down a space-time where the length of this curve measured from the outside, measured with respect to the faraway region is the same as the length of the same curve measured with respect to the near horizon region. So the two numbers have to match. The boundary conditions have to match.
What is the length as opposed to? I mean, that quantity is a local quantity. T prime squared plus t prime squared over z squared. That's a local quantity which depends on tau.
Yes.
But epsilon doesn't depend on tau.
Depend
Or
on.
does it depend on tau?
We set epsilon by hand, right?
Yeah, we set epsilon.
The scale of the boundary metric.
Yeah, it's the scale where that sets the cutoff. If you want, we could have chose here to parameterize t and z by some arbitrary proper boundary time u, and then I can always perform a 1D diffeomorphism
Okay, to make it constant.
this to be a constant, and then the big invariant thing will be to match the proper length on the outside for the proper length on the inside, and that would be it. Fantastic. So plugging this into here, well, to leading order, well, you can just write the formula really quickly. You get t prime cubed from this term, and then you get a factor of epsilon prime, epsilon squared, t prime squared, t double prime, divided by t prime squared plus epsilon squared t double prime squared to the 3/2. So notice that if I set epsilon to 0, so that's really the asymptotic ADS2 boundary, the extrinsic curvature of the near horizon region is just 1. But if I want to consider fluctuations from curves that are not precisely fixed, from curves that are not exactly at z equals 0, then I find that the near horizon extrinsic curvature is 1. Well, let me put back the factor of the ADS2 curvature. It's 1 plus epsilon squared times an object called the Schwarzian of t and tau, plus higher order terms in epsilon. The next term is epsilon to the 4th. Where the Schwarzian is the higher derivative functional t of tau that is given by t triple prime divided by t prime minus 3/2 t double prime divided by t prime squared. So in total, the action now just becomes, I had a term that was given by beta times m naught that came from evaluating the action in the faraway region. I had a term that looked like S naught that came from evaluating the contribution of a topological term in the near horizon region. And I have a final factor that looks like integral over du. The boundary metric square root of h u. The boundary metric is 1 over epsilon times the value of the dilaton at the boundary. That was phi b over epsilon times 1 over L2 times 1 minus 1 plus epsilon squared times the Schwarzian, and the minus 1 that came from evaluating the extrinsic curvature with respect to the vector pointing from the faraway region. So these simplify, and notice that now, so plus higher terms in epsilon, and higher and terms that are suppressed in 1 over S naught. So now I'm just left with something that's completely epsilon independent. Namely, this factor of epsilon squared cancels with these two factors of epsilon, and I'm left with beta m naught minus s naught phi b integral du. So sorry, let's call this t integral d tau from 0 to beta for Schwarzian of Pn tau plus corrections that are suppressed. So the point is that the entire effective field theory in higher dimensions, just the leftover thing is just an evaluation of the Gibbons-Hawking-York term that contributes something finite to the action that's epsilon independent, that's given by this higher derivative theory that's controlled by this action called the Schwarzian action. Great. And notice that the factor that appears in front of the Schwarzian action is this parameter phi b. And if you look back in your notes at what phi b was, it was precisely given by the breakdown energy scale inverse.
This is phi B or phi R?
Oh, sorry. This is phi. Phi b is the phi r over epsilon. Great. Thanks for telling me. Okay. So we want to now analyze the properties of this action and try to understand this model in more detail. So first, if that's precisely right. So there are counter terms that in principle you could set at the boundary of the faraway region, and those were actually needed when evaluating the faraway action. But in addition to that, there was a term, which is precisely this term, that you could view as the counter term that canceled this divergent piece in the Gibbons-Hawking-York term in 2D. And notice the second thing, it's important, it was actually important to keep track of the value of the dilaton at the boundary and take it to have a divergent value in order, even if we take it to have a divergent value, the action that we get is finite. So I hope that answers your question. And maybe the second observation that I'll make, going back to the initial JP action, why it's okay to set the value of the dilaton to be divergent in this case, but it's not okay in higher dimensions, is because that action is completely, the action doesn't have a kinetic term for the dilaton. So even if I set it to be divergent, there's no normalizability criteria for the dilaton that tells me that if I plug in phi that diverges at the boundary, the action that I would get or the type of fluctuations that I would get would be suppressed in the path integral. So yeah, so that's another reason why it's okay to set.
Can I do a similar thing? For example, if I take a D3 brand metric and I have an ADS5 process 5, and then I have opening up the class space. Okay, I can think about the size of this 5 as some, which is the equivalent of a dilaton, and then also have a blowing up dilaton from the perspective of ADS. If you just got the size of the S5, can I do a similar?
Yes, but I think you won't get any traction out of it, in the sense that I think if you evaluate the extrinsic curvature on surface that fluctuates a little bit, it would not scale as 1 plus epsilon squared. I think basically, unless I'm misremembering, I think the fluctuations of the extrinsic curvature are suppressed in the cutoff scale.
Remember, there's like this. There was a mode which was coming from embedding ADS into flat space. There's a singleton mode, which was coming by doing exactly this story. But okay, there are some papers in the early days of IPhT, and then people stopped working on that. So there's a singleton mode, which is expressing the overall embedding of the full ADS into flat space, and it was expressing. It's in a sense, when you have difference, you have a UN theory, and then you go from UN to SUN, and the leftover UN is the one that gives you this embedding. So there's some leftover U1 which was doing this thing, which looks very similar to this. So
I see. But do you remember was if you evaluated the Gibbons-Hawking work term at that surface, did it contribute a finite amount to the action, the fluctuation of the separation of the ADS-B?
I think that was supposed to be the U1. I mean, it's again the U1 part of the SUN. So I think it was finite, but then it just decouples from the perspective of IPhT.
I see.
I have to look. I mean, there's some old papers like Ferrara, Fronsdal, and
I see.
really old papers. It's
Talking
singleton.
about 2 plus 1 dimensions.
3 plus 1, 2 plus 1, whatever.
Okay.
So the singleton mode in IPhT.
There were whole papers on singletons where they discovered them by collecting all the damn boundary terms and supergravity theories and so on. And you wound up with degrees of freedom on the boundary. It's very similar in this experiment.
I see. Thanks for the comment. I didn't know about.
Luca, sorry, I feel like epsilon fourth, it's epsilon square in the last. You divide by 1 over f.
Yes. You're precisely right. Yeah. In the Lagrangian, in this expansion, it's epsilon to the fourth. But if I write it as a correction to the action, it's epsilon squared. But it doesn't really matter because I'm setting epsilon to 0 first. So that's in some sense the smallest parameter in the problem. Okay, great. So let's analyze some properties of this action. Maybe I'll analyze 2 property and then we can take a very quick break.
Can I just ask, how did you get 1 over s with 0 corrections?
Sorry?
Where did we lose them 1 over s 0 corrections?
So we lost them at multiple points. So one is when I expanded the action, the effective field theory, that was applicable in the entire space-time, that was written as a function of the dilaton chi. I expanded the potential u of chi, right, in the near horizon region. And that contains terms that are suppressed in S0. The second thing is that you can couple this theory to matter. Like in ADS2 cross S2, you have matter modes, and when you dimensionally reduce, you also have KK modes. And the mass of these KK modes is given by the size of the S2, which in this case is also given by, related to S0, right? It's the same as the radius of the black hole. And as I will explain a little bit later, even when you account for those modes, you do get corrections to the overall partition function. It's just that they will be temperature independent and only dependent on S0. So, okay. So what should we view as the coupling of this action? When can we evaluate this action by saddle point, and when can we not evaluate it by saddle point? And also, what are the saddle points? First, let's discuss the coupling. Naively, we would say that the coupling is this energy scale and breakdown -1. But, so this is naive. But a closer analysis tells us that the Schwarzian behaves very nicely under rescalings of time. Rescalings of what we call time. So suppose that I consider a new proper time on the one-dimensional boundary that's given by the variable u that is related to tau by u equal tau over beta. So if u is tau over beta and tau is beta periodic, then u is periodic with period 1. And now if I go from the variable tau to the variable u, you could look at this action and notice that because of all the derivative terms, essentially the entire Schwarzian action after this rescaling is multiplied by a factor of beta squared. Accounting for the change of variable 1 over beta squared, sorry. accounting for the change of variable in the integration measure, we get that integral d tau times Schwarzian of t and tau, 0 to beta, is equal to 1 over beta, integral from 0 to 1 du Schwarzian of t and u. So in other words, if I parameterize the proper time of my boundary curve of ADS2 to be completely independent of the temperature of the black hole that I had in higher dimensions, then I'm essentially just rescaling the overall action by a factor of 1 over beta. So since the thing that I'm left over with is just MSL2 inverse over beta times the integral from 0 to 1 du Schwarzian t and u. This is completely independent of any of the parameters of the black hole. So the only thing that controls whether or not I can evaluate this action by saddle point, or whether or not these equations, the equations of motion, completely fix t as a function of tau when I go to the low temperature limit, is this ratio. So this is the effective coupling of the theory, and it's very nice because it means that when the temperature is small, maybe it's convenient to put the temperature instead of beta. When the temperature is small, it means that this action is multiplied by a very small coefficient, and when actions are multiplied by a very small coefficient, I cannot evaluate them by saddle point. But when the temperature is much larger than this, oh, sorry, this is breakdown. When the temperature is much larger than this breakdown scale, then this coefficient is very large, and an action is well approximated by its saddle point, even at the level of a path integral. So essentially, the size of quantum effects in this effective field theory of near-extremal black holes is just controlled by this parameter. And this is completely in line with the observation that Preskill and collaborators made in the 90s that noticed that something wrong is happening precisely when this t times the breaking times the inverse of the breaking scale becomes order 1. Okay, maybe we can break for 10 minutes.
Light.
You're
You're on light.
Great. Okay, so we started studying this action. That's the effective field theory for the universal effective field theory for near-extremal black holes. As with any action, after we discuss the coupling, we should always ask what the symmetries of a problem are. So what are the symmetries of this action? Well, we just saw how this action behaves under one-dimensional rescalings of time. That's not a symmetry, but it was useful to understand what the actual coupling of the theory is. But let's also ask what the internal symmetry is. So first, let's actually go back to ADS2, which itself has an isometry, namely an SL2R isometry. Namely, if I take the metric written in Poincare coordinates and perform SL2R transformation, takes the following form: T plus minus IZ goes to A, T plus minus IZ plus B, divided by C, T plus minus IZ plus D, for A, B, C, D real numbers, and A, C minus B, D equal 1. I find that the metric itself is invariant under this SL2R transformation. So this is
AD minus BC, no?
Oh yeah, sorry. My bad. Great. Good. So now remember that to obtain the Schwarzian action, we had that z was equal to epsilon tau prime, which means that since this entire effective action is deduced by starting with the form of the metric and Poincare coordinates and parametrizing an arbitrary curve by some proper time, it means that to leading order in epsilon, the symmetry T of u going to A T of u plus b divided by C T of tau plus d should actually be a symmetry of the Schwarzian. And that's indeed the case. You can see here, well, if you plug in this, transformation for the parameter t in that higher derivative expression that I wrote down for the Schwarzian, you can actually see that I get back the Schwarzian itself. So this is just a cute property of the Schwarzian. However, one important point is that while typically in boundary theories, global symmetry, one should integrate over a phase space in which different points in phase space might be related by a global symmetry. Here, how the Schwarzian appeared was as a boundary term for a gravitational action. And if we want to do gravitational path integral, for instance, we should not overcount geometries that are the same. And geometries that are related by an isometry are just identical to each other, which means that when I eventually perform a path integral over curves of all possible shapes, T of tau, I should be careful not to overcount configurations that are just related by this SL2R isometry.
Right.
Yeah.
What about H tau tau, the induced metric? Is this preserved by?
Yes. It's preserved. It comes from the fact that the metric itself, ds squared equal dz squared plus dt squared divided by z squared is preserved. Mm-hmm. So automatically the induced metric, which here you replace dz by z prime squared and dt by d prime squared, that's also preserved. Okay. You can check explicitly. I promise if you plug in these functions back into the expression for the induced metric, you can check that it is invariant. So at this point, I just want to describe a little bit what these SL2R isometries are. Just to get some intuition about ABS2 space, ABS SL2R isometries map geodesics to geodesics. So geodesics are circles in ADS2. Sorry, let me draw it nicer. Are circles in ADS2 whose center is on the z equals 0 line. And more importantly for our problem, it also maps curves. So these have k equals 0. They're geodesics. And also importantly, it maps curves that are circles in the upper half plane to other circles that exist on the upper half plane. So circles that have their center in the that are entirely contained within on the upper half plane have the extrinsic curvature bigger than 1. Circles that touch the z equals 0 line have k equal 1, and circles that are in between have their center above the z equals 0 line, but some part of the circle goes outside of the upper half plane, have k smaller than 1. These are called horocycles, hypercycles, geodesics, and these don't have a name, even though, as we shall see, these are the most important for our problem. And the point is that these SL2R transformations relate all shapes that have the same extrinsic curvature. Let's discuss. Suppose that we want to look for a saddle point of this action that I just erased. What curve describes such saddle points? So, what are the equations of motion and solutions to the equations of motion? So, first, what are the equations of motion? Well, the Schwarzian action is a higher derivative action. So when we vary the action, we have to be careful because the Euler-Lagrange equations change in the presence of higher derivative terms. So, you could look up in Landau. In Landau, he has a derivation of the Euler-Lagrange equations for an action that only contains first derivatives, but a similar derivation applies to an action with an arbitrary number of derivatives, and one finds that the new Euler-Lagrange equation is given by the following: dl d tau minus d tau partial L partial t prime, the thing that's contained in the Euler-Lagrange equations. But in addition to that, if you have higher derivative terms in the action, you get the following terms in the Euler-Lagrange equations. You have to take derivatives of the Lagrangian with respect to t double prime, and derivative of the Lagrangians with respect to t triple prime. And this is set equal to 0. If you had an action that contained more and more derivatives, it's kind of clear what term you add. So this is just useful for your knowledge. If you ever encounter an even higher derivative action, you would add terms that look like minus 1 to the n, dn, d tau n, where this is your time, dl, dt n. But the Schwarzian derivative stops with has only a third order derivative, and that's why we only consider this term. Right? So one can write this equation, the resulting equation of motion, in a very compact form. Namely, the equation of motion that you get can be rewritten just as a derivative of the Schwarzian of t with respect to tau equals 0. Which means that the Schwarzian itself is a constant. But remember, the Schwarzian, what it was capturing was the extrinsic curvature of this shape. So it means that as constant Schwarzian action captures the solution is a curve that's just a circle in the upper half plane. It's one of these three curves, either the k equals 0, k equal 1, or k bigger than 1, or k smaller than 1. Yeah.
And so this saddle point to the.
So this is just a solution to the equations of motion.
So then this can embed back in 4 dimensions, where this will also be a saddle point of the 4D path integral.
Yeah. We'll see, in fact, that the saddle points match. Namely, it's kind of clear what this is, right? It's just that the extrinsic curvature on the near horizon region is a constant, which is just taking the standard near-extremal geometry and rewriting it into 2 different parts. separating the space-time into a near horizon part and a faraway region.
If I go to Lorentzian signature, these curves have a meaning. I mean, how can
Yes, they all have a meaning, though I have to admit I think I forgot how they look in Lorentzian signature. Yeah, I can tell you how. I can tell you afterwards. I can look at it. So here, this implies that the curvature in the near horizon region is constant. And in particular, since we want the induced metric to be the same and to have an expression that doesn't blow up at any point on the curve, the only option is to consider circles that are not intersecting with the asymptotic part of ADS2, so circles that are completely contained in the upper half plane. So k is a constant that's bigger than 1. We will actually come back to that, maybe in the fifth or fourth or fifth lecture. And one can write an explicit solution for T of tau by solving this equation, or by looking at what parameterizes circles on the upper half plane, and one finds that T of tau is given by tan I tau over beta. Or that's the same as tan by u. So plugging this into the action, one finds that the Schwarzian term evaluates to just uh, 2 pi squared t over m break. So essentially, you just plug this in back in here.
Sorry, Luca.
Yeah.
But it's a third order equation in T, and so you should have, say, 2 const, 3 const, 2 const, 2 free constants that you could add. So you fixed something there.
Yes. That's a fantastic question. So first, here I fixed a boundary condition that T of beta is equal to T of that T is periodic.
Okay.
Because I want my boundary curve to close, so that I'm describing a patch of ADS2. And the same boundary conditions I also impose for the first and second derivative of T. So those
periodicity,
are the periodicity of T and its derivative.
Okay, thank you.
So that's how you get these solutions without additional constants. Of course, there are also solutions related to these by SL2R transformations.
Yeah.
So I can apply, I can rewrite this function with an arbitrary ABCD, and that's the most general solution that I can find that's periodic. Okay, and this means that the total on-shell action, when just...
Can I ask a simple question? Does it bother you that T diverges? Does it bother the T diverges?
T diverges at...
When tau is equal, you get tangent of...
Yes. And I guess when... I think it diverges at 2 points.
Yeah.
And the meaning of this is that this is a very large circle, right? It has extrinsic curvature that is very close to 1, right? Because its extrinsic curvature was 1 plus epsilon squared, which means that the edges of the circle pretty much go all the way to infinity. This expression should be trusted up to corrections of order epsilon. And in principle, if I take the corrections of order epsilon, you would actually see that it's a circle that actually closes in the upper half plane, whose radius also scales with epsilon.
Does the curvature, so what's the value of the extrinsic curvature when you evaluate it on this?
Yeah. So it's this.
Okay.
Well, it's essentially the Schwarzian itself let's see, the source in itself just evaluates to this term. Let me make sure that I'm not saying something wrong. Evaluates, I think, to 2 pi squared t squared, or 2 pi squared over beta squared. And when you integrate from 0 to beta, this constant, you get this factor of 2 pi squared t over a breakdown.
I was just wondering, because you have, like, for extrinsic curvature you get a constant, so I presume that for every for different constants you get different geodesics, right?
Different curves that have k bigger than 1. Yes, yes, yes.
And what is the parameter that goes into the solution there? So the T of tau doesn't really depend on this curvature, or
T of tau determines the curvature. The parameter, the reason why this is the solution, what inserts beta in the solution are the boundary conditions, which is that T of tau has to be equal to T of tau plus beta. So this is how beta makes the appearance in the solution, and that's how the extrinsic curvature also depends on the temperature. Does that answer your question?
I'll think about it. So.
Okay, so with this, notice that the on-shell action, the overall action that we get by summing up the overall action for these black holes, is just minus beta m naught, that's not, minus 2 pi squared divided by beta m break. So if I were to just evaluate, to just say that this is the saddle point of a gravitational path integral, I would get that log z is minus this on-shell action, just like I did semi-classically before, and I would get this answer. And this was precisely the answer that I got for log z by literally taking the action of a near-extremal black hole, plugging in the full solution, and expanding it at small temperatures. So this is a very good consistency check that tells us.
It's something crashed. Go on, no problem.
Okay. So this tells us that indeed the Schwarzian action, the separation into 2 parts, still correctly captures the temperature dependence of the partition function. So how do we compute? We looked at the equations of motion and saddle points, starting from the action. How do we compute quantum effects in this? In the IPhT. Well, let's retrace our steps a little bit. So first, the path integral in the IPhT includes a path integral over the dilaton and the metric and all other fields for Matset. Of e to the minus this 2D action that depended on the dilaton and the metric, and the massive fields were suppressed in 1 over S naught, but we can still include them. So if I want to capture the dependence of the temperature in this path integral, I can again perform the integral over. I can perform the integral over the dilaton first, and since the dilaton appears linearly in the action, it still sets the curvature even when including quantum corrections. It just inserts a delta function in the path integral that fixes the Ricci scalar curvature to be a constant. And now the only thing I'm left over, is an integral over the metric. Well, the metric is fixed. It's just the metric of ADS2. The only things that remain unfixed were these shapes T of tau. So the thing that I'm left over with, if I want to correctly capture quantum effects is an integral over all possible curves that are parametrized by T of tau, e to the minus e to the m break inverse integral from 0 to beta du d tau Schwarzian of t and tau, where in front of the action I have this factor of e to the s naught minus beta m naught that came from fixing the background far away from the black hole. So this is the path integral that I would like to solve for. So to compute, let's first look at what this integral is in a quadratic expansion around the saddle point that we previously found. Yep.
Right. Is the plus sign in the exponent?
Yes, because the Schwarzian itself appeared with a minus sign in the action. So e to the minus the action, the Schwarzian appears with a plus sign.
It's not definite positive anyway.
Sorry?
Schwarzian is not positive.
Well, as we shall see, it is.
It is.
It is, yes, yes. By positive definite, you mean that when you expand the Schwarzian to quadratic order around the saddle point, the quadratic order has has negative coefficients in the exponent.
Okay, okay.
And this is precisely what comes out.
It's the sign that doesn't lead to some instability.
It's the sign that doesn't lead to some instability. Well, it's the sign that comes out of the calculation of integral of k, but that is also the sign that does not lead to an instability. Yeah, let me make sure that I didn't make a typo earlier. No, at least in my notes, I had that the Schwarzian was with a minus sign in the action. I don't know if I wrote it wrong on the board, but okay. Good. So let's expand T of tau as a tan I f of tau divided by beta, where f of tau takes the classical value tau plus some small fluctuation epsilon of tau, where the fact that the variable t is periodic with period beta implies that the variable epsilon is also periodic with period beta. So this is the perturbation. This was the saddle. And this is the quantum fluctuation. Okay. So I can expand my fluctuations into Fourier modes that are normalized on the circle. And importantly, there are free modes that I will not include, namely the modes that infinitesimally correspond to the Fourier modes with n equal -1, 0, and 1. And I'll explain why just in a second. Let me write exactly what those modes correspond to. So the modes with n equal -1, 0, and 1 correspond to the constant mode and the first Fourier modes. And the reason why I should not consider them in this path integral is because if I perform an SL to R, an infinitesimal SL to R transformation on T of tau, it turns out that an infinitesimal transformation of T of tau turns on either the mode epsilon 0, epsilon 1, or epsilon -1. So essentially, if I only want to integrate over configurations that are distinct, that are SL to R, that are not related by SL to R transformations, then essentially it's enough to set epsilon 0, epsilon 1, and epsilon -1 to 0. This might seem like a tiny detail, but this is actually where the physics of this path integral. So
Does that mean that there should be some volume of SL2R somewhere when like just to divide by the volume of the gauge group?
So here, maybe I should tell you what the integration space is. The space T of tau is the space of curves that parameterize a circle. So it's the space of functions. You could think of about the space of functions T of tau as being T plus 1. And to get rid of configurations that are equivalent by an SL2R transformation, I divide this this integration space, I quotient this integration space by the SL2R transformations that I wrote earlier that act on T by sending T to A T plus B over Ct plus D. Maybe in some sense the volume factor of SL2R is associated to the fact that there's a quotient in the integration space for the path integral. Okay, so now I can just plug this guy into the action, into the Schwarzian action, and expand it to quadratic order. So I get that the action itself, I total fluctuating is given by 4 pi squared divided by m breakdown times t times the sum of starting at n strictly bigger than 1 of n squared times n squared minus 1 times epsilon minus n epsilon n plus terms that scale like epsilon n cubed. Parameter terms in epsilon. So related to your question, notice that in the action, all these modes appear with a positive coefficient at quadratic order. N squared minus 1 and n squared are positive for n bigger than 1, which means that in the path integral, these quadratic modes are well defined. Well, one can perform an integral over them without needing to change contours. The important thing to notice is that whenever we have a quadratic integral for quantum fluctuations, that tells us how peaked quantum fluctuations actually are. So the coefficient in front, just as before, is this effective coupling that's given by T over m break. So when T over m break is very large, so that's black holes that are further away from extremality, these fluctuations, Gaussian with very large coefficient has very suppressed fluctuations, which means that all the geometries that contribute the most in the path integral are just the ones with k equal constant. But once I go to smaller temperatures, these modes epsilon n and epsilon minus n are no longer peaked around 0. They have a very wide spread, which means that configurations that have the boundary very wiggly all contribute about the same amount. And here, notice that higher loops in epsilon are also multiplied by the exact same coefficient, T, by the exact same effective coupling. Okay, so the conclusion from all this is, so far, we have seen that extremal black holes are actually not trustworthy saddles. Why do I say that? Well, a trustworthy saddle is one around which all fluctuations are suppressed by a large parameter, right? That's the definition of a saddle point. However, here we see that when the temperature is small, this thing can become arbitrarily small, and the fluctuations can become out of control. So now let's actually evaluate this path integral over the modes epsilon up to one loop order. So for that, I have to write what the measure is. The measure for dt comes from the path integral measure for the metric in higher dimensions, which in turn can be assumed to come from an ultra-local form for that measure. And in terms of the variable t of tau, when you expand things in these modes epsilon, what this measure ends up evaluating to is a product from n bigger than 1 of 4 pi n cubed minus n d epsilon n d epsilon minus n.
Is this some assumption about the UV completion of the 4D gravitational theory, or?
No, it just assumes that the measure in 4D takes an ultralocal form, which implies that in 2D it also takes an ultralocal form, and this implies the specific form for dt of tau.
Yeah, I guess I'm trying to get a sense of how much this ultralocal form in 4D is
Is determined.
Yeah, like by some UV completion should tell you what is the path integral measure in 4D.
Yes, but I don't know.
We don't know what it is.
In any case, in this specific case, the choice of measure will actually not be very important. I'll explain why in a second. That's one of my comments. So our calculation doesn't usually depend on the choice of measure, but let's see what we get. So now the partition function is given by e to the minus beta m naught plus s naught plus the on-shell contribution of the Schwarzian, which evaluated it to pi squared t over m breakdown times this integral over d epsilon n, d epsilon minus n, this stuff comes from the measure, e to the minus this expansion, the action at quadratic order. Now, this is just the Gaussian integral, where this is the coefficient of the Gaussian. So importantly, notice that there are modes that are absent that would have had 0 weight in the path integral otherwise, namely the modes with n equals 0, 1, and minus 1 have a vanishing coefficient at Gaussian order here. The meaning of that is that the extrinsic curvature doesn't change under an SL2R transformation. So the action itself should not change under the SL2R transformation. But the consequence of that is that when I integrate over all these modes, in total, I find, so here I get the same as what I wrote on the row above. And now the integral over each mode just gives a factor of t over m breakdown inverse the factor of n squared times n squared minus 1 precisely cancels with this factor of n cubed minus n when you take the one loop determinant, and you're just left with a factor of n. So in total, you're left with 1 over 4 pi squared e to the minus beta m naught plus S naught plus 2 pi squared T over M breakdown. So now we have to regularize this infinite product over all the modes. And the way to regularize it is to consider the ratio of two of these partition functions, in which case you find that effectively the one loop determinant is given by 2 pi times T over M breakdown to the free half. So notice that here, to obtain this result, when you take ratios, you could do zeta function regularization. And the power of free halves appears precisely that because if I would have taken the product over all n's of this term that goes like 1 over T times M break, I would have gotten something that is temperature independent. But because these free SL2R modes are absent from our path integral, I end up with a power of free halves that precisely counts the number of zero modes that this action has.
Sorry.
I was going to say, it's a function of 1 over T M break. So how did the T and the M break get separated and then into a product regularization?
Oh, sorry, I may have made a typo here. Yeah, sorry, the T and M break is here. Right, because it's the coefficient of the Gaussian is just T over M break, so the one loop determinant is just takes the same form. Thanks for noticing. Yeah.
Luca, you said that you wanted k greater than 1 intrinsic curvature. But does this imposes a constraint on the quadratic modes, on the epsilons? I mean, I wonder if you should put some constraint in the functional integral. It's really a Gaussian.
Yeah, so here, when you consider like the Gaussian integral, there's no constraint because even if you fluctuate it a little bit, the circle still doesn't, leave the
K greater than 1.
The K greater than 1 space. And I don't think, I think even if we consider an integral over the entire dFS1, as long as it's an integral over dFS1 and not some other boundary condition, and not another function that doesn't have periodic boundary conditions, then I think we're still only including circles that are fully contained in the upper half plane.
Okay.
Well, perhaps I'll make a comment. We'll see later that there are certain geometries that in some cases we will include that have negative extrinsic curvature on the boundary. But in that case, what will happen is that such geometries will have a handle in the near horizon region. I'll mention that later. It's a bit premature. Okay. Notice that, so the first thing is that the power of T was related to the number of zero modes. So it was related to the number of generators of this SL2R isometry. This is what gives the number of zero modes. And notice that factors like the 1 over 4 pi squared or whatever change of measure I would have chosen here only changes the constant in front of the partition function, and this constant can be absorbed in a redefinition of the extremal entropy S naught. The important thing is that here this constant is independent of the charge and temperature of the black hole.
Yeah, I could have done something much more brutal in this integration measure by having some epsilon n dependent, in which case you would not have just Gaussians over epsilon.
Sure.
Yeah.
Well, yeah, then probably your measure, especially if you have other factors of epsilon n inside it, would come from something that would not have a local expression in terms of the metric, I would guess, because you would couple, you would just couple different modes to different ends, which means that somehow your measure couples fluctuations of this near horizon region that have one shape to those that have a completely different shape. And finally, I should mention that there is a magical aspect about this path integral, which is that this one loop expression that I wrote down is actually the full answer to the partition function to all orders in this coupling T over M break. So if I were courageous enough and wrote the next order term in epsilon and computed the next correction in T over M break, you would find that it vanishes. And if you did it more and more and more, you'll find that higher and higher orders vanish. And this is explained by the fact that the integration space itself for this path integral is a symplectic space. And there's a very nice argument that was developed by Stanford and Witten, which explains that because the integration is a symplectic space, one can do a procedure called fermionic localization that shows that the partition function of this theory is one loop exact. It's an argument that's not quite as simple. It's not as simple as the fact that this is a symplectic space. You also need to understand what sort of killing vector generates flows in this symplectic space. That turns out to be the Hamiltonian of this Schwarzian action, and that's enough to show that the Schwarzian partition function is computable using localization. So if we weren't able to do that, we would have a problem in understanding the low temperature behavior of near-extremal black holes, right? Because we see that as the temperature as T over M break becomes smaller and smaller, higher and higher loop corrections can become more and more important. But luckily, since it's one loop exact, this means that we're fully capturing the temperature dependence for these types of black holes. So now let's analyze the answer a little bit before we go to lunch. So first, what is the ADM map? The expectation value of the mass. Well, since I have the partition function, I can just use the standard thermodynamic formula, which tells us that the mass is the extremal mass plus 2 pi squared and c squared over m break plus 3/2. So let's plot this just like we plotted the mass above extremality in order to formulate puzzle 1. So here is m extremal. So previously, classically, we found a quadratic function. This was semi-classical. And there was a paradox related to this, which was that the emission of a single Hawking photon is enough to make it such that these black holes that are very close to extremality cannot even evaporate. Now that the shape of the expectation value of M is lifted, and it looks something like this. So this is with quantum corrections. And in particular, it means that these black holes that now, when you include quantum corrections, can always evaporate to become extremal. So in this sense, At least schematically, it seems like the paradox or the problem, the thermodynamic breakdown that Prescott and collaborators brought up is resolved by including this factor of 3/2 that comes from the one-loop determinant.
Sorry, the fact that you have 3 in 3/2 is related to the fact that you have 3 zero modes.
Yes, yes, exactly. It's related to the number of SL2R generators, which gives the number of zero modes. Great.
Is the 3/2 important? Could any linear behavior work here?
So that's why I said it's schematically that it resolves the paradox of Prescott and collaborators to fully address the. It's clear that the breakdown of thermodynamics. So this is the scale and breakdown. It's clear that the breakdown of thermodynamics is related to the fact that these quantum effects become important. So one should no longer trust the thermodynamic calculation. But in order to actually understand how these black holes evaporate, you would need to recompute what the rate of Hawking radiation is in the presence of these quantum effects. And that has not yet been fully done. The entropy is given by S0 plus 4 pi squared T over M break. This was the semi-classical answer, but the entropy I'm just computing using the related thermodynamic formula minus 3/2 log T over M break. This is the one loop correction that captures that. This is the one loop correction that, notice, can become very large when T over M break is very small. Namely, when T over M break is very small, it could dominate over this correction that's linear. Oh, sorry, I think there's a factor of plus here that it's not a minus. Okay. So while the entropy initially looked linear as a function of the temperature, now, so this is S0. Now, as I approach the scale M breakdown, the answer deviates from the semi-classical answer because this piece dominates. And in particular, for temperatures that are very small, my entropy can be drastically reduced compared to the extremal entropy. So this addresses puzzle 2. Because now we see that the extremal entropy can be radically modified by the presence of these quantum corrections. And the left plot addresses puzzle 1, which was about the breakdown of thermodynamics.
What makes us make of the fact that this is divergence because there are result is one with effect. So
Right, great. So this result is a perturbative result in 1 over g Newton. So in principle, what we didn't account for are corrections that are non-perturbative in 1 over g Newton. For instance, there could be completely other saddles, or even configurations that are not even connected to saddle points that we don't have control over, that provides non-perturbatively small corrections. So this brings me to the question, what is the regime of validity for the formulas that I wrote above? And one can argue that the perturbative expansion of all other modes, of the massive KK modes that I ignored in the path integral, don't give you things that diverge as the temperature goes to 0. So the regime of validity for these formulas are when the temperature is first when the black hole is extremal, black hole is near extremal, which means that the temperature is smaller than 1 over RH, which is equal to 1 over Q. It's still valid when the temperature is smaller than this other scale, M breakdown. But it might become invalid when non-perturbative effects become important, or when T scales like some number, perhaps like 1 over RH, times e to the minus 1 over g Newton and something. So in particular, if the regime in which t, if I take t to scale like e to the minus s naught, for instance, that's the regime in which I shouldn't trust this formula anymore. I'm not sure, there's no control that we have over it, but we can be confident that up to the point where other saddles or other geometries become important, the entropy just keeps decreasing and it's decreasing at extremality. So how about the density of states? Another way that we phrased the past puzzles was in terms of what happens to the density of states close to extremality. So the density of states can be just obtained by taking a Laplace transform, or an inverse Laplace transform of the partition function. So the density of states is defined for this relation. So we can take a Laplace transform of the formula for the very simple formula for the partition function that I wrote earlier. And what you find is a very simple formula for the density of states as well. That's very revealing. It goes like 1 over m breakdown times e to the s naught times sinh of 2 pi square root of 2 times e minus m naught divided by m breakdown. Okay, so let's analyze a little bit the analytic behavior of this function. So at very large energies, so here's m breakdown. At very large energies, the function grows like e to the some number times square root of e, which is precisely the type of state growth that you expect for black holes due to Cardy's formula and many other arguments. However, as we approach extremality, the density of states goes to 0, and eventually, in the regime close to E equal m naught, which is the origin of this axis, the density of states behaves like square root of E minus m naught. Yeah, here I should put e to the square root of E minus m naught. So instead of having an exponential behavior as you approach the origin, as the semi-classical prediction would have said, so the semi-classical prediction would have been in red. Once I go to energy scales that are closer to extremality than this breakdown scale, the behavior of the density of states completely changes and goes to 0 as I approach extremality. So the regime of validity that I discussed before is up to energies that are exponentially small compared to the scale m breakdown. So it's up to very, very small energy levels. So the regime of validity is in this entire interval, well, all the way here. So I should say that the only thing that I rely on in my derivation is that I look at what But fields in my two-dimensional effective field theory became massless in 2 dimensions and performed a full path integral over them. And that doesn't depend on the number of space-time dimensions of the original black hole or whether the black hole was in flat space or ADS. It only depends on the presence of these modes, which came just from the fact that the near horizon region is ADS2. And that's true regardless of the nature of the full space-time. And just as a final comment, here, in some sense, we've resolved puzzles 1 through 3. We now see that the breakdown of thermodynamics is related to the fact that quantum effects become important in the near horizon region. We've seen that the entropy of an extremality can become, as we approach extremality, can become arbitrarily small. And we've seen that the density of states is highly affected at small energies. And this helps us make sense of the ADS2 CFT1 relation or ADS2 CFT1 duality as just some sort of effective duality between near-extremal black holes and the Schwarzian theory. So perhaps I should contrast the density of states that we got here starting at the zero energy or the energy above extremality to a density of states that one would get for a higher dimensional theory in ADS. In higher dimensional ADS, one would get this discrete spectrum of energies above the lowest ground state. So you get the vacuum, and then you have matter excitations that are gapped, as I described in the first talk. So this is energy equals 0. This is the first mass, 2m. You can form higher and higher particles. And black hole microstates only populate the spectrum at very high energies. Here we see that in ADS2, essentially I have infinitesimal small excitations that I can turn on, but nevertheless I can account for their density of states by studying the Schwarzian theory. I should finally mention that even though we accounted for an infinite order of corrections in T over M break, right? Even though the answer is one loop exact, that means that if we would have written the corrections and this is the answer to all orders in T over M break, even though we did that, the density of states that we got is still continuous. It's not a sum over delta functions. So while this resolves puzzles 1 through 3, it does not resolve puzzle 4, which is about the discreteness of the black hole microstate spectrum. Okay, thank you very much. Let's go for lunch.
Yeah, maybe we have time for some questions if you want.
Yes. Maybe. So you mentioned that this is also valid in ADS.
Yeah. And higher dimensional ADS, I mean.
Right, but so I was thinking that because in gauge supergravity or in asymptotically ADS spaces, I can have black holes which have not the spherical horizon, but like some general Riemann surface. And then the assumption of dropping the massive modes, like this, I can see how this works on the S2, but maybe on some Riemann surface, I would have to keep track of those.
Of additional zero modes.
The KK modes, like, or
that could be zero modes.
Yeah. But I don't know if this.
Perhaps I will describe later that, for instance, if there's if after the KK reduction you have let's say even a massless scalar field, which I think is what you would get if you had these higher Riemann surfaces that have moduli. Even in those cases, those fields, including the quantum effects of those fields, doesn't correct the energy dependence of the energy of the density of states. It only corrects the overall scale of the density of states. So remember that the density of states is multiplied by e to the s naught. In principle, here I did not include logarithmic factors in S naught. That's what I'll actually do in the lecture in the afternoon. In principle, this gets corrected by S naught to some power.
The shape remains, yeah.
But the shape in terms of the energy remains the same. It just gets rescaled. Yeah.
I have two confusions. First of all, you were saying before that the energy in this 1 plus 1, 0 plus 1 universal CFT has to be more like, delta function of E plus 1 over E.
Right.
That doesn't look like...
Exactly. And that's because the Schwarzian theory is an EFT that's not a 1D CFT. If you look at SL2R transformation, is not a space-time symmetry, it's a global symmetry. What I mean by that is that in a CFT, conformal transformations act on the space-time. One of the conformal generators is the Hamiltonian, let's say, while here, SL2R transformation acted on the mode T of U, and it didn't act on U itself. And the interpretation of that so that just means that it's not a 1D CFT. The interpretation of that from the bulk perspective, from ADS2, is it comes from the fact that the boundary conditions that we were forced to impose at the edge of the throat explicitly break at the SL2R invariance that I see at extremality. For instance, in the leading order saddle has a non-trivial profile for the dilaton, right? I wrote the formula for what the dilaton is as a function of U and V. And if I do an SL2R transformation on that profile, I don't get an invariant answer. So it means that the dilaton getting a non-trivial profile breaks the SL2R isometry that exists in ADS2, and that in turn occurred due to the fact that I put different boundary conditions for the dilaton at the end of the throat.
I just wanted to add, I understand that you don't like the fact that the density of states is not a sum of delta functions, but do you understand the square root behavior of the...
You mean at
I don't know, physically?
Yes. Perhaps that will come up again. The square root behavior is extremely common in chaotic systems. It's one of the first signatures of chaotic systems. It's not a guarantee that by any means that you have a chaotic system if you have a square root edge. But for instance, the square root edge is also encountered in all one-cut matrix integrals. So perhaps it's a first sign that the system that we're describing is chaotic all the way down to extremality.
Okay. The square root comes from which mathematical property of the partition function?
It comes from the fact that at very low temperatures, the one-loop determinant dominates in the partition. It's the leading temperature dependence in the partition function. And if you take the inverse Laplace transform of a power law, you also get a power law. So the inverse Laplace transform of t to the 3/2 is just square root t. Right.
So it's directly depending on the number of zero modes that you have in the...
That's right. So, yeah, go ahead.
No, I wanted to ask, so if I change the number of zero modes that I have in the system, then the behavior at zero energy would be different, or the behavior at M0 would...
Yes. We will in fact see an example of that in the afternoon when we study supersymmetric black holes instead of these black holes that only have an SL2R isometry in their near horizon region.
So you don't get a square root for this?
You do not get a square root for supersymmetric black holes. In fact, the spectrum of supersymmetric black holes that you get from this computation will in fact also partially address puzzle 4. Good. Yeah.
So you just said the square, we know that the square holds up to t equals to 0, but didn't we before that say that at t equals to 0 we can't quite trust?
Oh, sorry. I meant that the regime in which the square root holds is up to energies that are exponentially small in 1 over g Newton.
Okay.
That's when non-perturbative effects can change this this result, assuming this is the leading saddle to begin with. But we don't know other saddles, so. Well, we know some, but they're subleading in 1 over g Newton. for instance, multi-center black holes or crazier things like that are subleading in 1/3 Newton compared to this result. Any other questions?
Yeah, maybe the virtual room, video conference. No? Okay. Okay, so we go to lunch. We will meet again at 3 p.m. this afternoon, and
So we
in
leave from the
15
lobby,
minutes we start.
and we go to lunch in 5 minutes from the lobby. 15 minutes from the lobby.
10.
Let's put 10. Let's put 10.